Welcome to Maths with EJD once again, and we've been doing a series on matrices. This video is going to focus on special matrices as we consider in pairs. We'll consider singular and non-singular matrices. Then we'll consider symmetric and skew symmetric matrices. We'll consider lower triangular and upper triangular matrices. We'll also consider nilpotent and idempotent matrices, as well as orthogonal and unitary matrices. So they are special for a reason, so you see very soon. Interestingly, all of these matrices have to be square matrices. That is one thing common to all of them. Okay. Now, going to page 2, the second slide, we talk about singular and non-singular matrices. And as we see there, a square matrix A is singular if its determinant is 0. So if the determinant of a matrix is 0, then you say it's a singular matrix. And you remember in the last video, I told you that once a matrix does not have a determinant, then you cannot find its inverse. And once you cannot find the inverse of a matrix, it means that the system of linear equations that will arise from that matrix will not have unique solutions. So this is pretty important. And examples of matrices that are singular would be the null or zero matrix with elements zeros all the way. So if you find the determinant, it just gets 0, you know. And then you have, of course, this is not a special matrix, matrix B, 3, 0 minus 2, 0. But I mean, it is singular because once you find the determinant, 3 times 0 minus 0 times minus 2, the answer is 0. So that makes it a singular matrix. So in short, a singular matrix is a matrix whose determinant is 0, basically. And then that takes us to the idea of non-singular matrix. Again, a square matrix A is non-singular if its determinant is non-zero. That is, if you can get a value that is not 0 for the determinant of a matrix, then that matrix is said to be non-singular. It means that since it is non-singular, it can be inverted. It is invertible. You can find its inverse. So the unit matrix, 1001 or any other unit matrix for that matter, has a determinant of 1, and because of that, you can say that a unit matrix is non-singular. In the same way, if you have this matrix C, 3, 2 minus 2, 1, the determinant 3 times 1 minus 2 times minus 2 ends up giving you 7. So that means that matrix C is a non-singular matrix because the determinant is non-zero. Very important. And then I go to the next set, talking about symmetric and skew symmetric matrices. Again, it has to be a square matrix. A square matrix is symmetric if it is the same as its transpose. If it is the same as its transpose. If you find the transpose of a matrix and what you get is still the matrix you started with, then you say that that matrix is symmetric. For instance, matrix A is 3, 2, 2, 5. If you transpose it, transpose means that you change the row to column and column to row. We've done that before. So row 1 is 3, 2. It becomes column 1, 3, 2. Row 2 is 2, 5. It becomes column 2, 2, 5. So this way you see that they are basically the same. So you can, in that case, you can say that matrix A is a symmetric matrix. So the same is applicable to this matrix B. If you find its inverse, B transpose here would have to be first row is 4 minus 1, 2. So it becomes 4 minus 1, 2 as first column here. Second row is minus 1, 7, 0. It becomes second column here. Third row is 2, 0, 6. It becomes the third column in the transpose. So, and by the time it's all done, you can see that they are basically the same. So in that case, you can say that B is a symmetric matrix. And then we go ahead to talk about skew symmetric matrix. A square matrix A is skew symmetric if its transpose is equal to the negative of the original matrix, right? So if you take the transpose of a matrix and you end up getting something that is the negative of the matrix you started with, then you can say that that matrix is a skew symmetric matrix. For instance, you have C is 0, 2 minus 2, 0. If you transpose it, 0, 2 becomes 0, 2 here. Minus 2, 0 becomes minus 2, 0 here. If you apply minus to it, it ends up as the matrix. The transpose is such that if you take out minus 2, then it becomes minus into 0, 2 minus 2, 0, what you started with. So the transpose is equal to the negative of the matrix. Then the same is applicable to D, right? So you have 0, 3 minus 1, minus 3, 0, minus 2, 1, 2, 0. If you transpose it, row 1 becomes column 1, row 2 becomes column 2, row 3 becomes column 3. And then if you take the minus out, like you factorize minus 1, kind of, then you end up getting the matrix you started with. So that the transpose of D is minus D. So that is a skew symmetric matrix. Interesting. Okay, so we go to the next. We have the lower and upper triangular matrices. Again, a square matrix, L, is lower triangular if all entries above the main diagonal are 0. So you already know the main diagonal is the diagonal consisting of elements 1, 1, 2, 2, 3, 3. So every element above that, if every element above the main diagonal or the principal diagonal is 0, then you say that a matrix is a lower triangular matrix, So so you can see this L1, 3, 5 is the main diagonal. So above that, you have 0. So as a result of that, you can say that both L1 and L2 are lower triangular matrices. Now, if you are finding it difficult to interpret this, it means that if you have IJ, so for every I less than J, you have Lij equals 0. So that means, let's say that, this is, of course, it can be element 1, 1 because I and J are expected to be different. So if you have 1, 2 now, 1, 2 is 0. As far as I is less than J, so your 1 is less than your 2. So, and you see, that's what you have here. This is like L1, 2, L1, 3. This is L2, 3. 3 is greater than 2. For every such element where the number of the column position is greater than the row position, and it is 0, that you can say that is your lower triangular matrix. So you have the reverse for upper triangular matrix. So a square matrix U is upper triangular if all entries below. So now for upper it is above, but now for lower triangular you have zeros above. For upper triangular you have zeros below. So a square matrix U is upper triangular if all entries below the main diagonal are 0. Where all the UIJs for. Now I greater than J. So here you have something like where you have the zeros now. This is like U 2, 1. So you see the number of rows is bigger than the number of column. So you have U3, 1, U3, 2. So the number of rows is greater than the number of column. That's what this expression UIJ equals 0 for every I greater than J means. So below the principal diagonal, you have zeros. Below the principal diagonal, you have 0. So that means U1 and U2 are both upper triangular matrices. All right. So that takes us to the next set, talking about nilpotent and idempotent matrices. A square matrix N is nilpotent if there exists a positive integer k such that n raised power k is 0. So if you have a matrix and you raise it to a particular power, it doesn't have to be 1 or 2, it doesn't have to be 3, it can be any integer, right? Any positive integer, say 2, 3, 4, 5. So if you raise a matrix to a particular power and you get a zero matrix, a null matrix at the end of the day, then you say that the matrix is a nilpotent matrix. For instance, S equals 0, 1, 0, 0. If you square that, you have 0, 1, 0, 0, 0, 1, 0, 0. Of course, I already told you, you write this one twice because there are 2 rows here. So you write each of these columns twice. So you have 0, 0, 0, 0, 1, 0, 1, 0. And then you invert this one over it. 0, 1 over the first row, 0, 1, 0, 1. The second one, you invert it over it, 0, 0, 0, 0. Now, by the time you multiply each of those components, right, you have 0 each, 0 times 0, 0 times 1, that's 0. 1 times 0, 0, 0 times 1, 0. Add the 2, you have 0. Everywhere like that is 0. So you can now say that S is nilpotent. So the same happens for T, 0, 1, 0, 0, 0, 1, 0, 0, 0. So if you square that again, so we are able to find the particular integer k equals to for the first one, for k equals to for the second one. So by the time you also multiply these two, you get a zero matrix at the end of the day. So if you can get a particular integer k and you put it as the power of a particular matrix, and the matrix gives you a zero matrix, then you can say that that matrix you started with is a nilpotent matrix. All right. So that takes us to idempotent matrix. So a square matrix P is idempotent if P squared is equal to P. So when you square the matrix, now here it is specifically square. If you square a matrix and you end up getting the matrix back, then you can say that the matrix is actually idempotent. So for instance, the unit matrix will always be idempotent. It's just like if you square 1, if you raise 1 to power 2, it will always give you 1, right? So you can say the unit matrix for any order, maybe order 1, order 2, like what we have here, or order 3, like that is idempotent, because if you square it, like as expressed here, the same way like I've explained here, if you square it 1 times 1, 1, plus 0 times 0, that everything is 1. So this is 0, this is 0. The last one, 0 times 0, 0. 1 times 1, 1. So you end up having a unit matrix that you started with. So you can say every unit matrix is idempotent because their square will give you back what you started with. So we also have this matrix U, which is not a square matrix, which is not a unit matrix. It's just it looks like it, but it's not exactly, because this here is 0, not 1. So you have 1 0 0 0 1 0 0 0 0. If you square it again and you follow the procedure, right, because there are 3 columns here, so you write each of this one 3 times. 1 0 0. So you see 1 0 0 1 0 0 1 0 0. Same. 0 1 0 0 1 0 0 1 0 0 1 0 thrice. 0 0 0. You have 0 0 0 0 0 0 0 0 0. Then you invert this one on top of it. That's why you have 1 0 0 for the first row. You invert it all through. For the second one, 0 1 0. So you invert it 0 1 0 all through. And for the third one, 0 0 0. So you invert it all through. So by the time you do all that and you multiply things out, you end up having this matrix U back. So you have 1 0 0 0 1 0 0 0, and that gives you what you started with. So now you've squared U and you ended up getting U back. So you can say that matrix U is actually idempotent. Okay. So let's go to the idea of orthogonality, orthogonal matrices. A square matrix Q is orthogonal if its transpose is equal to its inverse. So the transpose of a matrix is equal to the inverse of that matrix. Then you say that the matrix is orthogonal. And because it is orthogonal, right? So it means you have Q transpose is equal to Q inverse. We already know that if you multiply a matrix by its inverse, you end up getting the unit matrix. So if you multiply this inverse by Q, of course, it means you have to multiply this one by Q. And since Q inverse Q is going to give you the unit matrix, so you can say that if the Q transpose times Q gives you the unit matrix, then that is establishment of the fact that Q is actually orthogonal. Okay. So, for instance, you have this matrix P, and you're told to establish whether it is orthogonal or not. So the first thing you have to do for two matrices to be orthogonal, it means that the matrix multiplied by its transpose will have to end up giving us the unit matrix. So of course, the transpose of this, of course, 1/3 is outside, so that doesn't affect anything. So you can transpose what is inside. So you have 1 to 2 column 1, row 1 there becomes column 1 here. 2 1 minus 2 becomes 2 1 minus 2 here. Minus 2 2 minus 1 becomes the column here, right? And then so you can now have your normal P, and this transpose is what you have here. So now to multiply the two together, of course, you can multiply the 1/3 and 1/3, put them outside, and then these two matrices are now side by side. Then you follow the rules, because there are 3 rows here, right? You write each of these columns 3 times. So that's why you have 1 2 2 1 2 2 1 2 2. Then write 2 1 minus 2 3 times, 2 minus 1 2 1 minus 2 2 1 minus 2 2 1 minus 2, 3 times like that. And then lastly, minus 2 2 1, write it 3 times also, and then you put this over it, 1 2 2. So you have 1 2 2 all through the row, and you have 2 1 minus 2 all through the second row, and then you have this third row will come over the third row here. And once you do all that and you multiply out, see what you get. You get you get 1 times 1, 1, 2 times 2, 4, 2 times 2, 4, 4, 4, 1. That's 9 here. Then 2 times 1 is 2. 1 times 2 is 2. That's 4. 2, minus 2 times 2, minus 4. 4 minus 4, 0. Minus 2, 4, minus 2. Minus 2, 4, minus 2. That's 0, And then you have 1 times 2, 2. 2 times 1, 2. That's 4 minus 4. You get 0. 2 times 2, 4. 4 4 plus 1, 5, plus minus 2 times minus 2, that's also, this is 4, right? Minus 2 times minus 2 is 4, plus 4, 8, plus this 1, so you have this 9. Then minus 4, 2, minus 2, so that is, that's minus 4, 2, and 2. So that ends up giving you 0. That's minus 4 plus 2, that's minus 2 plus 2, that's 0. Then here, you have minus 2, 4, minus 2, that is 0. 2 times minus 1, that's minus 2. 1 times minus 2, that's minus 2. That's minus 4 plus 4, 0. Then again, this also gives you 0. Minus 4, 2, 2, that's 0. And lastly, minus 2 times minus 2, that's 4. 2 times 2 is 4. That's 8 now. Plus minus 1 times minus 1, that's 1. That's 9. So, and previously, you already had 1 over 9 outside. 1 over 9 outside. So if you take the 1 inside to divide, so 9 divided by 9, that's 1. 0 divided by 9, of course, is 0 all through. So 9, all these divided by 9, you have the unit matrix. So at the end of the day, you see that the P times the transpose of P is giving you the unit matrix. So that is to establish that since P transpose is the unit matrix, then you can say that P is orthogonal. P is orthogonal, like that. That's how to establish that idea. So we take one more example on that. So you want to show that Q is orthogonal, right? So you have cos theta 0 sine theta 0 1 0 minus sine theta 0 cos theta. And of course, the transpose will just be cos theta 0 sine theta will end up in cos theta 0 sine theta. That's the transpose. 0 1 0 becomes this, minus sine theta 0 cos theta ends up being this. And once you have taken care of all that, then you can now say QQT transpose. Of course, it should be that QQT is the same as QTQ, and all that should be equal to I. You can check this middle one out. That's what it should be. So here now you have Q, you have the transpose of Q. And of course, you go ahead and do the multiplication the same way. So 1, 2, 3 rows. So you write this one 3 times each. So cos theta 0 sine theta, cos theta 0 sine theta, cos theta 0 sine theta, then 0 1 0, you also write 3 times, 0 1 0, 0 1 0, 0 1 0, and then minus sine theta 0 cos theta, write that 3 times, and then you invert this over the first row. So cos theta 0 sine theta, cos theta 0 sine theta, cos theta 0 sine theta, then you have 0 1 0, that goes all through, and then minus sine theta 0 cos theta also goes, minus sine theta 0 cos theta, minus sine theta 0 cos theta, minus sine theta 0 cos theta. And once all that is done, then you just multiply out and add them up. So cos theta times cos theta is cos squared theta. I'm going to take trig somewhere along the line. Trigonometry that will come along the line. So cos squared theta times cos squared theta is cos squared theta. Then 0 times 0 is 0. Sine squared theta, sine theta, cos theta times cos theta, right, is cos squared theta. 0 times 0 is 0. Sine theta times sine theta, that's sine squared theta. So you have cos squared theta plus sine squared theta. Then 0 times cos theta, 0. 1 times 0, 0, 0. So everything ends up being 0 here. And here you have minus sine theta cos theta. That's minus sine theta cos theta. Sine theta cos theta sine theta. That's sine theta cos theta. Of course, this is 0 there. So you have this. Then here, this is cos theta times 0, 0. 0 times 1, 0. Sine theta times 0, 0. That's why you have this 0. And here also, you have 0 times 0 is 0. 1 times 1 is 1. 0 times 0 is 0. So you have 1 there. Then minus sine theta times 0, 0, 0, 0. So all this goes to 0. And then lastly, you have cos theta times minus sine theta. That's minus sine theta cos theta. Then sine theta cos theta. So you have minus sine theta cos theta plus sine theta cos theta, right? And then, of course, here, 0 times minus sine theta, that's 0. 1 times 0, 0, 0 times cos theta is 0, And lastly, you have minus sine theta times minus sine theta, that's sine squared theta, plus cos theta times cos theta, that's cos squared theta. Now, in trigonometry, there's a rule that sine squared theta plus cos squared theta equals 1. So when I teach trig, I'll maybe give you one or two proofs of this. So as a result of that, this cos squared theta plus sine squared theta is 1. There's 0 here already. The minus sine theta cos theta plus sine theta cos theta, minus plus, that'll be 0. Then you have 0, 1, 0 there already. So minus sine theta cos theta plus sine theta cos theta, that's 0. Then you have the 0 here. Then sine squared theta plus cos squared theta is also 1. So at the end of the day, you end up getting the unit matrix. So that means that Q is orthogonal. Q is orthogonal. Since QQT equals I, so that is the idea of the orthogonal matrix. So that takes us to the idea of unitary matrices. Well, we will not have to waste too much time on this because I'm not going to talk about matrices with complex entries, maybe that'll be another topic on its own. So, but I mean, I'll just mention it. So a unitary matrix is a square matrix. It's a square, you can see all of them as square matrices with complex entries. So it has complex entries. When you talk about complex entries, you have maybe I, which is the square root of -1, or some people use J, which is square root of -1, right? So that's for complex numbers. Maybe I'll also teach complex numbers one of these days. So a unitary matrix is a square matrix with complex entries that satisfies the condition of being unitary when its conjugate transpose is taken. So in that case, a matrix U is unitary if the conjugate transpose U star is equal multiplied by U equals U star is equal to the unit matrix, where U star now is the conjugate transpose of U, and I is the identity matrix, like we've always known. So here, I'm just going to run over this because I'm not going to spend too much time on it. So here now, this is your matrix U, so which is 1 over root 2 into 1, 1 minus 1, 1. And, this is the conjugate transpose, which is U star. So 1, 1 becomes 1, 1, minus 1, 1 becomes minus 1, 1 here. So that's the conjugate transpose. So the same happens here. So V is 1 over root 2. 1 minus I, this is not 1, this is minus I, and minus I means square root of -1. Then 1 minus I 0, I 1 0, and then 0 0 root 2. So by the time you transpose all that to 1 I 0, this is 1 minus I 0, that is 1 minus I 0, then row 2 becomes this. So you have -1 0. I think it's not just the transpose per se. Yeah, so we have that example. So 0 0 2 also here. I might be mixing up something here. I'm not sure about this minus. So, but just like I told you, I'm not dealing with complex matrices. I don't see the use for it. It's not that commonly talked about, So, but then this looks very close to the idea of orthogonal matrices, but except that this one talks about complex entries. So, I mean, this one, I'll have to check to be sure if that is what it should be. So, so with this, we come to the end of special matrices. I know you've learned a lot. So if you have questions, please ask in the comment section. If you have topics in mathematics you'd like me to teach along the line, let me know about it. And then I might be able to do that. Thank you so much for listening. See you in the next video where I talk about echelon form. I think that's a very interesting topic in mathematics, echelon form. See you then.